Okay, so welcome back to another video. Here we have a limit that we want to evaluate. So we have the limit as n approaches infinity and everything in the inside is going to be dealing with is natural logs and factorials. So we have n times the natural log of n factorial divided by n minus the natural log of n plus 1 factorial divided by n plus 1. So this is one of those things that a lot of the stuff that we're dealing with is just we're reducing it down easier to by utilizing properties of both the natural log and factorials. So if we can actually do it in a way that it's easier to actually reduce down to our answer, eventually one of the last things we're going to do is that we're actually going to convert this entire thing into an integral using its Riemann sum definition in terms of a limit. And well, if we can do that, then we can actually convert this into a definite integral, which of course that will make things a whole lot simpler for there. But what that integral will look like is, well, you're gonna have to stay tuned and find out. So with that, why don't we actually just jump right in? So first thing I'll do is let's actually get everything in terms of a common denominator, and I'm going to multiply the n into everything on the inside. So applying this, I have the limit as n approaches infinity. So all this, so that means I have n and n times n plus 1 just to get that common denominator over here. And then the natural log of n factorial, and so divided by, so n times n plus 1. And then subtract, so then I multiply the n here, but multiply the n for over here as well. So then that'll become n squared, and then the natural log of n plus 1 factorial, and then all this being divided by n times n plus 1. Okay, so of course, as you can tell, that we have some things that are going to cancel. For one thing, I'm actually going to cancel out the n's for all this. But because there's an n plus 1 over here, what I'm going to do is I'm actually going to distribute the n plus 1 term into multiply that to our natural log of n factorial. So after applying this, so I have limit as n approaches infinity, so then this will become now n, then multiply by the natural log of n factorial, and then add this with the natural log of n factorial, and then now subtract, so one of the n's will cancel, so then I'm just left with n and then multiply by the natural log of n plus 1 quantity factorial. All this for our common denominator is simply just going to be divided by n plus 1. So as you can see, there's some things that we can actually utilize some natural log properties. You can see I have a natural log, or n times the natural log of an input, and then subtract. So what that implies is that I'm actually going to apply the natural log properties, but at the same time I'm also applying the natural log, or applying the factorial properties of n factorial divided by n plus 1 factorial, since that's the subtraction. And what that'll do is that's actually just going to cancel and just leave it n plus 1 on the denominator. So basically we have the limit as n approaches infinity. So now this is going to be n times the natural log of 1 divided by n plus 1. And then so we have our plus the natural log of n factorial, all this being divided by n plus 1. Okay, and so now what I'll do here is, yet again, I'll apply another natural log property. So this is 1 divided by n plus 1, so that's the same thing as the natural log of 1 subtract the natural log of n plus 1. So that term can move to the back of the subtraction. So then limiting it down, so I have n approaches infinity. So rewrite this, I still have the natural log of n factorial, then subtract n times the natural log of n plus 1, and then all divided by n plus 1. Okay, so now going on to our next step, what we're going to do here is our n factorial. We're going to actually just by definition just expand that out just a bit, just so you can see the picture of what we're going to do next. So now that means natural n of n factorial is of course 1 times 2 times 3 all the way up to n. So the limit as n approaches infinity, so then I have the natural log of I'll just write this as 1 times 2 times 3 all the way up to n, and then minus n times the natural log of n plus 1, and then all this being divided by n plus 1. So now here's the interesting thing on how we're actually going to do this. So this kind of looks a little confusing on how we're going to reduce this down. And by the way I explain this, it kind of looks like it's an incorrect way of doing it, but you'll see where I'm going with this picture. So equals, that'll be later after the explanation. So here's what I'm going to do. So we're actually going to have the natural logs. We're actually going to combine that together into a single natural log logarithm. Then afterwards, expand that as a sum of natural logs. So to see the bigger picture over here, so the natural log So if I were to combine this together into a single natural log, you'll notice that, so of course the numerator is going to be 1 times 2 times 3 all the way up to n, but I have an n times the natural log of n plus 1. Why can we do that? There's no n associated with this one. Well, n is the same thing, of course, as if you move it to the front, that's going to be your exponent. So you're actually multiplying n plus 1 n times because of that exponent. So then n plus 1 times all the way up to however many times n of n plus 1. Close that off. And then what you can do is we can actually apply the, so we have everything in terms of multiplication, and then I can actually just separate it out. So we're actually doing it in terms of associating with the n plus 1 for each of the natural numbers up above. So in other words, I can write this as a sum of natural logs in the following. So ln of 1 divided by n plus 1, then plus the natural log of 2 divided by n plus 1, then plus 3 divided by, or natural log of 3 divided by n plus 1, so on and so forth, all the way up to the natural log of n divided by n plus 1. Okay, so we can utilize this and then substitute this back to over here. So then now the limit as n approaches infinity, so then this entire thing will be written as the following. So I have the natural log of 1 divided by n plus 1, add this with the natural log of 2 divided by n plus 1, all the way up so on and so forth to the natural log of n divided by n plus 1. So of course, all this still being divided by n plus 1. Okay, see? So that's pretty neat. So how do we actually continue on forward here? Let's actually do a little substitution. And no, we're not doing, integral substitution, u substitution. We're just doing a simple substitution just to replace some things out. So let's actually, oops, push my door. We'll let u equals n plus 1, okay? So then this entire thing is gonna replace with the limit as n approaches, or in this case, it's gonna be in the world of u, but it'll still approach infinity anyway if you actually do the substitution. So after all this, I have the natural log of 1 divided by u, add this with the natural log of 2 divided by u, all the way up to plus the natural log of u subtract 1 and then divided by u. Yeah, see, because if we actually just substitute that, okay? And then so all this being divided by u. But that wouldn't make sense exactly to the fact that you said that we would actually convert this in terms of an integral just by judging how the function's designed. How can we? There's no other way we can actually do this. There is actually. We're going to add and subtract a 0 term. So to expand this out even further, I have in this case, we're gonna have the natural log of u divided by u, and then subtract this with the natural log of 1 over here, okay? And so, yep, they're both natural log of 1s, and then minus 1 is still gonna be 0. This will be 0, so that can actually, getting a little creative here, we could just ignore this term. But however, the natural log of u divided by u can be written as the same thing. Well, this entire expansion of the numerator, I'm saying, is that now this is gonna be the limit as u approaches infinity of 1 divided by u multiplied by our finite sum from n is equal to 1 to u of the natural log of n divided by u. Okay, and guess what? By utilizing the Riemann sum definition based on our finite sum and everything in terms of breaking up into some intervals, this is the same thing as the definite integral from 0 to 1 of the natural log of x dx. And of course, if you know how to evaluate this, we know that indeed this is by utilizing integration by parts. So I'll just save that step for, you guys can verify it for yourself and see that this is going to be x times the natural log of x subtract x. Evaluate this from 0 to 1. Of course, if I just plug in 1, then it means this whole thing is simply just going to be -1. I plug in 0, that's going to be a 0, but over here, natural log of 0 is undefined, so of course you would have to do this in terms of getting into indeterminate 4 and then applying L'Hopital's rule and get that the entire thing when you plug in 0, then the whole thing is going to approach 0. And so therefore, this entire limit that we're actually evaluating is simply just going to simply approach to just -1, which is the final answer, just like that. And everything, of course, utilizing factorial's natural log properties, getting a little creative with here, but mainly over here specifically for this term over here. Then we get our definition Riemann sum that we wanted to, get into an indefinite integral we wanted, an easy one to calculate. Calculate the bounds, there's our answer, just like that. So yeah, that's pretty cool if you ask me.